This is an introduction to increasing and decreasing functions, exercise 6.1 on page 235 of your textbook. As I mentioned, we're focusing on the idea of derivatives, we're focusing on the idea of stationary points as a brief introduction, because that's the next exercise, and I'd like to, of course, talk about increasing and decreasing functions. Let's start with derivatives. With derivative, of course, we know that derivative function represents the gradient of the tangent at that point, right? Of course, that will change over time, but we can use that to our advantage. But for now, we need to identify what a positive negative gradient is and when we need to restrict a domain in order to always have a positive gradient, a negative gradient, a zero gradient, etc. It's a very common exam question. Of course, we already know that this is a positive one, this is a negative, right? But the difference between these two we need to identify as well. This one, of course, has a gradient of 0, and this one here is undefined. Okay, so we have our different gradients there. A very common exam question would look like this. If I have a function that looks like this, identify for what values of x, and it will say something like this. The derivative is greater than 0, and we need to identify the domain or restrict the domain so that that is true. In this case, f dash x represents our gradient. In this case, greater than 0 means a positive gradient. Of course, that's going to be this section to this section, right? I'm going to write an incorrect answer, and I just want you to tell me why. Good? So, positive gradient, of course, is going to be the middle, so I'm going to go from -1, so x is an element of -1 to, and I'm going to say the value here, that's 5. Why is that incorrect? It's a very loud bird today. Say it one time. At the bottom, there is a gradient, but the gradient is 0, isn't it? Yes, stationary point. Good. If it's a stationary point, the gradient should be 0. At x equals -1, it should actually be a curved bracket. I'm assuming that's what you're going to say, wasn't it? Yeah. So it should be a curved bracket. And this one is going to go from the gradient being less than 0, right? So again, I'm going to write an incorrect answer. I want you to tell me why. So it's going to go from negative, right, towards this point here, and then it's going from this point down towards the right as well, right? So it's going to be x is an element of from -infinity all the way towards -7, and then, of course, a union with 6 towards infinity. Why is that incorrect? No, I think it's fair, like, because you don't explicitly need the arrows, but it's a cubic function. We've been given a cubic where we know that it's got a negative gradient from the very left towards the first stationary point, and the stationary point on the second right-hand side towards infinity. They're all negative. But why is this wrong?
Because it's not actually straight.
Nah, the answer's a lot more obvious than you think it is.
It's the y.
I've written the y value. Good. It should be the x value, right? From -infinity to -1. And, of course, 5 to infinity as well. Yeah? Any questions? Okay. Last example here says whether derivative equals to 0. Of course, that's our stationary points. I'm going to do the same thing. I'm going to write something wrong, something that students get wrong all the time, and I want you to tell me what I've done wrong. So, it says f of x is equal to 0. I know, of course, it needs to be my x value, and it needs to make sure that I've included only those values here. So x is an element of, and I'm going to write, I know it's going to be when x equals to -1, so -1 and 5. Why is that wrong? So if I do the square brackets, let's say I use the square brackets. Why is that still wrong? You're right, it is an issue with the brackets, but why is that still wrong? What does this actually say? Good, interval from -1 to 5. I'm not saying all of this is going to have a gradient of 0. What's the correct bracket I should be using? Curly brackets, good. You can either write it as this, or you can just write x equals to -1 or 5. They both suffice, but make sure you're not sending the wrong message with the incorrect brackets. Any questions? Okay. As a quick recap, of course, positive, negative, and an equal to 0 gradients means that we can identify different stationary points. If we want to find a stationary point, we just let it equal to 0. And of course, to identify the nature of the stationary point, we'll do that in the next exercise, okay? But I do want to focus on the next point, which is a local versus a maximum. I'm going to skip forward to 16. Here we go. We're going to do a very brief introduction to stationary points. I want to make it very clear. There are, of course, your maximum turning points. So that's going to be your max right here. You've got your local minimum, right? This one right here is what we call, of course, a point of inflection, right? We already know that. It's a point where the gradient goes towards 0 and then changes. However, while stationary points can be points of inflections, not all points of inflections are stationary points. So not all points of inflections are stationary points. So this one right here, of course, is pretty obvious. The gradient is 0 at some stage. Done. Happy. This right here, I'm going to try and draw that a bit better. That one right there technically still is a point of inflection, but it's not a stationary point. Just be very clear when you're identifying points of inflection, especially because later in the year when we do our calculations on the CAS calculator, so I said CAS and point at the broccoli, but the CAS calculator, when we graph it, it will identify specific points as points of inflection that aren't necessarily stationary points. Okay, so just keep that in mind. Okay, so we've got a point of inflection. Of course, we find the stationary points of the following functions. In this case, of course, I'm just going to solve or find the derivative first. Sorry, so dy dx, nothing fancy, no product rule, anything necessary here. I'm just going to rewrite that as negative 4x plus 12. I'm going to let my dy dx equal to 0, which gets me an answer of, adding that on both sides, 4x equals to 12, x equals to 3. Don't make the mistake of substituting back into the derivative function. What will I get if I substitute x back into the derivative function? 0. 0. Exactly right. Don't make that mistake, yeah? Sometimes the coordinate is indeed 0. In this case, it probably isn't. So we substitute back into this function, and we get y equals to 9 plus 12 times 3 minus 2 times 3 squared, which gives me an answer of 9 plus 36 minus 2 times 9, or in other words, minus 18. Alright, that gives me 45, 45, that's 35, 35 gives me 27. So the coordinate itself is 327. Now, in this case, we just find the stationary points. In the next exercise, we'll look at the nature of stationary points. But there are a few ways you can do that. Any questions about this? 2 more points before I get you started. Absolute max, there we go. Apologies. Absolute max. So the difference between these two, I'm 100% cutting that out, by the way. So the difference between a local max and an absolute maximum, yeah? So in this case, I can see that on this function, the local max is this point right here. Easy, done. The absolute maximum probably isn't in this case. Because imagine if I haven't given this function a domain, this function would continue on forever, wouldn't it? Well, technically, while the local maximum is that point A, the absolute maximum is wherever the function has its highest point, which is not necessarily at a stationary point. Let's say that what I've drawn, the purple lines, that is our new domain. Let's say I restrict that to as a domain. The absolute maximum would be this point right here. If I remove that, and I just look at the red line and anticipate that as my restricted domain, well, in this case, the local max and the absolute maximum would be the same. Any questions? Last concept. I'm going to write this down here on the bottom right. So we're looking at strictly increasing and decreasing. So strictly increasing and strictly decreasing. Apologies for the horrible handwriting. So for this part, what we're going to focus on is this right here, and I'll write down here. If A is less than B, then f of A is less than f of B. If a is less than b, then f of a is less than b. In other words, if a function is strictly increasing, it just means as we go towards the right in the more positive direction for x, we're going to get a value that's increasing. So generally speaking, the gradient's always going to be positive. That's what that means. And of course, inversely, if a is less than b, then f of a is greater than f of b. I'd like you to take note of this terminology that I'm using. I know it's super basic, but it will come back later on. When we do pseudocodes, when we look at pseudocodes later on, if-then blocks are very important. If this, then that. Okay? But again, that will come up later in the unit. Strictly increasing, again, it probably just looks something like this. Again, that depends on what your function is. It doesn't have to be a perfect linear equation. It can be curved as long as within your set domain, which you might need to restrict yourself or identify, you're always going to have the next value being higher than the previous value as you go to the right, and of course inverse as you go towards the right as well for decreasing. That's it. Any questions? Okay, I didn't get a chance earlier to show you another common error that students make, but for this question up here, question 11, another common mistake that students make is to use the wrong brackets and do a square brackets for a negative infinity. Just a reminder, of course, you can't actually reach negative infinity or include it, therefore it's just the curved bracket. Okay?